Hello everyone, I am Yamini. My project is on time series forecasting of air quality in Santa Clara using AI models. In this presentation, I will be covering the motivation behind choosing this topic, related work, problem statement, modeling, results, challenges, future work references. So to start with, is it necessary to monitor air quality? As we all know, air is an essential part of life, making air quality control crucial for public health. Air pollution leads to serious health issues, including respiratory and cardiovascular diseases. It has both long term and short term effects. Children, elderly, and those with pre existing conditions are particularly at risk. However, even healthy individuals can be adversely affected by poor air quality over the period of time. Apart from its impact on public health, it also has serious impact on environment and economy of a country. It affects the wildlife, damages forests, and impacts water bodies. Air pollution also contributes to some of the broader and serious environmental phenomena like acid rains and atmospheric deposition. On the economic front, the costs are substantial. Healthcare expenses increase as more people suffer from pollution related illnesses, placing a financial burden on individuals. Additionally, it also leads to loss of productivity, affecting businesses and leading to economic slowdown of a country. A study by Stanford shows that air pollution costs the US economy around 5% of its annual GDP in damages. The highest cost come from early deaths, which can be attributed to exposure to fine particulate matter, which are measured as PM2.5. The related work. The time series forecasting is divided into two main categories: classical methods and advanced methods. Classical methods include models like ARMA, ARIMA, etc. Advanced methods are further divided into machine learning and deep learning. Machine learning models include SVM, decision trees, KNN, etc., out of which SVM is the most popular and widely used method. Deep learning models include RNN, GRU, etc. There has been studies which focus on combining classical methods with advanced methods like ARIMA with SVM, ARIMA with neural networks. So, the problem statement. The project aims to improve public health and environmental quality by developing machine learning models that can accurately forecast PM2.5 particulate levels in Santa Clara County, California, using the air quality parameters like air pollutants, which include nitrogen oxide, sulfur dioxide, ozone, etc., along with meteorological conditions like precipitation, temperature, etc. The main community contribution through this project is to alert the public and health officials to implement effective air pollution control strategies, to monitor and manage the long term impact of pollutants on ecosystems and public health. The data set is from the California Air Resources Board, which collects data on the amount of pollutants emitted from different types of sources, as well as the concentration of these pollutants in the air and weather conditions. So, the air quality parameters are divided into two broad categories: air pollutants and meteorological factors. Air pollutants include ozone, nitrogen oxide, sulfur oxides, etc. And the meteorological factors include temperature, dew, precipitation, etc. So, I have sourced the hourly data spanning 5 years from 2019 to April 30, 2024. For the input features: nitrogen oxide, sulfur dioxide, carbon monoxide, ozone, dew, precipitation, temperature, humidity. And the target variable is PM225, which is PM2.5. So, to better understand the correlation between different variables and the spread across different years, I have performed data analysis. And as the data contains variables which are measured at different scales, I have performed min-max scaling to avoid any scale induced bias. Further, I've imputed the missing values using the daily average, but there were cases where there was no data recorded for the entire day. So in that case, I've used the linear interpolation. I have experimented with traditional models like decision trees, KNNs, and XGBoost. And under neural network models, I have experimented with RNN, LSTM, and GRU. Through the data analysis, I found that carbon monoxide, sulfur dioxide, nitrogen oxide, which constitutes the air pollutants, are more positively and strongly correlated with PM2.5 compared to other meteorological factors, with CO being the highest and most positively correlated with PM2.5. In this graph, we can see that nitrogen oxide follows some seasonal trend where its levels are highest during the first few months and the last few months of the year. SO2 doesn't show any seasonal patterns, only there are for it suddenly the levels of SO2 suddenly rise in 2019 and 2023, but that too is for a short period of time, maybe for a day or a week. Carbon monoxide again follows some kind of seasonal trend like nitrogen oxide. And precipitation is usually higher in the first half of the year. In PM 2.5, we can see that there is uh, no constant or any visible trend. But we can see that in 2020, the later half of the year saw a spike in PM 2.5 levels. So for decision tree KN and the XGBoost, which are constitutes our traditional models, the input data should be in the form of samples, comma features. But whereas for neural network models, the input data should be in the form of data, comma one, comma features, where one represents the time step, and the output or the target variable y is in the form of samples. I use the train validation test split of 60 is to 10 is to 30, where 60% of the data is used to train the model, 10% to validate the model, and 30% to test the model. To find the best parameters for decision tree, XGBoost, and KNN regressor, I have used the hyperparameter tuning with grid search CV with CV set to 5. I found that for decision tree regressor, the best parameter for maximum depth is 6. For XGBoost regressor, the best value for n estimators is 50. For k nearest neighbors, the best value for parameter k is 30. Then the RNN, LSTM, and GRU constitute the three main neural network models I experimented with. In RNN, the output variable YT depends on the internal state ST, which in turn depends on just two variables, XT, which is the current input at timestamp T, and ST minus 1, which is the previous internal state. But RNNs face the vanishing gradient problem. So to address these problems, LSTMs introduce a extra cell state CT minus 1. So in this case, the internal state ST depends on three parameters: the previous cell state CT minus 1, the previous internal state ST minus 1, and the current input at timestamp T XT. And to further address the vanishing gradient problem, GRU is introduced, which is a variant of LSTM. The novelty of GRU is the introduction of the three gates: the update gate ZT, the reset gate RT, and a third gate S tilde RT. So each gate plays a different role in controlling how to filter, use, and combine prior information. Uh, the results on the test data for the window size of 12, 24, and 48 to predict the future time steps of 1 or 3 time steps. So here the windows are measured in terms of hours. So 12 hours, 24 hours, 48 hours. And this is to predict 1 hour into the future. So the values show that increasing window sizes don't consistently lead to better or worse performance, suggesting a complex relation between historical data and forecasting accuracy. XGBoost show a good balance between the MAE and RMSE scores, consistently performing well across different window sizes and future steps. This indicates robustness due to its ensemble approach, which effectively reduces variance and bias. Deep learning models tend to have high errors compared to tree-based and XGBoost methods in some setups. This might suggest overfitting or that these models require more fine-tuning, more data to better model the complex features in the time series data. Shorter future steps, simpler models like for shorter future steps, simpler models like Decision Tree and XGBoost perform well compared to the neural network models. And in deep learning models, there is no consistent trend, but we can see that for smaller window sizes, LSTM performs better most of the times compared to GRU and RNN. But for the large window size of 48, GRU consistently performs better across any number of future time steps. Here we can see that for window size of 24 hours, that is 1 day, and to predict future time and to predict 3 time steps into the future, XGBoost has the best forecasting, best performance with least error metrics. It can also be seen in the data that the forecasted test data is following the similar trend as actual test data. In decision tree, we can see that there has been a spike in the forecasted test data where the actual data value is less. In this case, I have plotted the decision tree for window size of 1 to predict future time step of 1 hour. So each node has a set of values. In this case, the first line is the feature and the threshold. This tells us which feature and what threshold value are being used to split data at this particular node. This being the root node, the samples are equal to the number of training samples. This is equal to the length of the training set. So, for example, this carbon monoxide less than equal to this particular threshold indicates that the data at this node is split based on whether the carbon monoxide level is less than this value or not. And the value here represents the information gain. So, as the number of samples are more here, the information gain is less. But as we go down to the leaf nodes, the nodes become more pure, leading to increase in the information gain, which is also evident from the color encoding. So these are the results with neural network models. We can see that with window size of 24 hours to predict 3 time steps into the future, LSTM has the best performance. You can see that GRU is not performing well. It's uh, somewhat predicting more values than the actual test data. To better understand how the neural network models come to a particular decision or reach to a particular decision, I have employed the XAI, or which is also known as explainable AI technique, using the LIME tool for the model LSTM. And for the test point, for the last test point, that is on April 30th, at the collected at the last hour at 11 p.m. So in this graph, green bars represent features that push the model's prediction higher push the model's prediction higher, and the red bars represent features that push the model's prediction lower for the target variable. So the green bars where humidity is for this humidity T at time step 30 and time step 35 are less than uh, these values contribute positively to the model's output. This could mean that humidity values at time step 30 and 35 less than these threshold values 51.8 lead to higher predicted values of PM 2.5 levels. And the negative bars, the negative contribute lead to negative contributions. So these bars show that certain conditions related to carbon monoxide at time step T and temperatures at time step 3419 below a certain threshold or exceeding a certain threshold are driving the prediction lower. For example, lower CO levels at current time step and specific temperature conditions significantly impact the predictions of the PM 2.5 levels. So the main challenges in time series forecasting for air quality is that the data is not available for every particular region. It's only collected by the government weather collection status. And the challenges which I faced are getting the raw data from the government websites where the data is stored separately for different parameters, and combining the data for all parameters into one data set was challenging, and modeling with different type of models like standard models which include decision trees, knns, and modeling with neural network architectures uh, was challenging because the data handling and the modeling procedures were different. My future work include better hyperparameter tuning for neural network models too, and to develop a dashboard or application to forecast the results in real time so that the government and the people can get get the real time information, and to develop more robust machine learning models for time series to better predict the future future air quality. These are the references.